Okay, so the Arrhenius example is really just a suite of physical chemistry equations where simultaneous equations can be applied to. And there are lots of equations. You can probably think of some yourself. But as another example, I'm going to look at the Van 't Hoff equation, or the Van 't Hoff isochore, describing the equilibrium constants K dependence on temperature. So the Van 't Hoff equation, or at least a precursor to it, says that the natural log of the equilibrium constant K is equal to minus the change in enthalpy for a reaction divided by RT plus the change in entropy of the reaction. This is derived, if you want to have a look at this, from the equation ln K is equal to minus, delta G is equal to minus RT ln K. Okay, so here we have two unknowns. We have the delta H value and we have the delta S value, the enthalpy change and the entropy change. So if we measure the equilibrium constant at two temperatures, we can solve the simultaneous equations that we generate for delta H and delta S in almost the same way as we did for the Arrhenius example. So let's look at an example. Here we have the equilibrium constant K at two different temperatures, and the results are shown. And we're going to use this data to determine the enthalpy and entropy of the reaction. So I'm going to write out my equation again, except this time I'm going to put in the values K1, T1, so there's two equations because we have two temperatures. So again, you can see when I subtract the second equation from the first, my delta S value disappears. I can now put in the values that I have from my experiment, and when I rearrange for delta H, I get a value of 459 joules per mole. Now that I know delta H, I can put the value back into one of my equations. So here I'm putting it back into the first equation to give me a value for delta S. So you can see there's very strong similarities between this example and the example we looked at in the for the Arrhenius equation. One small caveat here is that there is a little problem in that we have reciprocal temperature values here. So we're dealing with very, very small numbers, and experimentally it's probably better to look at a range of different equilibrium constant values over various temperatures and plot a graph of ln K versus 1 over T, and the slope of that graph would be minus delta H over R, and the intercept would be delta S. But if we just have two values, we can use this method here